Hi, welcome back. And here we are again. As you can see, a lot of coloring has gone on in this section of the tube radio schematic. What that means is that a fair amount of checking has been done. Everything that's been painted green has been gone through, and what I said the last time is that I'm going through this in phases as usual, with the power supply being the stage that I was going to do next. But obviously from the schematic you can see that I've gone further back before the actual AF stage. But what I want to talk about today is just the AF stage. The reason I go back is when you start checking, you get on a roll, and it's actually not a good idea to stop, because setting things up again can be a pain. So if you're there and the capacitor's in your way and it's part of this circuit, simply because you're doing that one, hey, just do it. It gets done. It's painted in. It's less work you need to do when you go back to the IF stages. So that's why you see quite a bit of painting that's gone on here. And if we focus back onto the AF stage, into the power amp stage, the important thing was to start at the input where the audio comes in. Now, there's a switch here which selects between the radio audio and the pickup or tape audio coming in. You can see the tape, the pickup would go here through a 47K resistor to that switch. This would be the input from a tape deck, again direct to that switch. This means that you can either use that one or that one as an input for an MP3 player or a Bluetooth receiver or whatever you want. That one just gives you a little bit more drop because of the 47K resistor. But anyway, it goes in there and you have a fair amount of circuitry afterwards before it leads off from the wiper of the volume pot to the first triode there, that triode in that EABC80, which acts as an AF amplifier, preamplifier. So what we end up with here is various resistor capacitor networks, which I want to actually go through. And the reason I want to go through this is because I wanted to understand them myself. I've always been very curious about the tone controls on some of these German radios. And some of them are almost impossible to figure out logically. This one, fortunately, is actually quite simple. So I'm going to just go do a few experiments and show you some of the conclusions that I've arrived at as to how some of those push-button preset tones work. There's one here, and there's another one over here. They're on the front of the radio, as I've shown before. But we'll get into that in a minute. What we end up with here is the signal coming in goes through that switch, and when selected, you have a divider network here, which is 47K with 2.2 meg in series. And what that does is it drops the level for a tape input if you wanted to record this. Now, these radios had a tape DIN jack which served as tape in and tape out. That's the reason you got those two resistors over there. Once it gets in there, it goes through a coupling cap, 10 nanofarads, and then you end up, it goes into this box here with a network of resistors and switches. That is one of the tone control presets, which I'm going to explain in a minute. It then gets to the top of the potentiometer, the volume pot, and that is connected through a 270 to ground. So this is the top and that's the bottom of the pot, as it were. There's the wiper, and off it goes into the preamp. Once it goes out of the preamp, it comes out of the preamp triode. At the anode, there's a 47K resistor. Then you have the B plus coming in here, and your audio's over there. It's coupled with a 10 nanofarad capacitor to this section, which again is a tone shaping section of the circuit. It acts as, this is another one of those preset tone controls, which again I'm going to show you in detail. And it goes into the grid of the power amp power tube, the L84, at pin 2. This one is cathode biased with a 250 ohm resistor to ground and a 50 microfarad capacitor decoupling it. Gives you more gain and so on, and more bass. It comes out of the anode and you're into the output transformer. The grid is connected as before, the screen grid is connected as before when I discussed the power supply. Some of these indications here, 260, 243 in blue and red, these are some of the voltage readings that I've been doing both on AM and FM sections. And I cannot really conclude much from that yet because they're a little high. They are quite a bit higher than they're supposed to be. This is supposed to be 241. Now I'm not sure what the schematic means, whether it's on AM or FM, and it does make a slight difference. I get 259, 261. There's an even bigger difference. This is supposed to be 227 and I get 243 and 260, but it's working fine and I want to show you it working. But just before that, I want to discuss this feedback system. What it does, you take the output signal through another tone shaping feedback network, which then feeds to the bottom of the volume pot before the bottom, because you've still got a 270 to ground. So whatever's feeding back is actually subtracting from or adding to the level of your wiper on the volume pot. So this is acting as a negative or positive feedback system. My guess is it's negative. We just have to see, because you're dealing with an inversion here, an inversion there. I would imagine this is negative feedback, or you'd get howling like crazy, but what it does is it feeds back certain parts of the signal, tone shaped. So again, you get tone control affecting your signal going in before it then comes back out through the volume pot wiper to your preamp. So let me show you a little bit more on the actual radio, what I've done here. Most of what I've discussed and what I've shown you there happens at this section of the radio. You've got the volume pot down there. There's the volume pot. You've got some of those capacitor resistor networks connecting to the volume pot, which goes to the feedback system. There are quite a few coupling and shaping capacitors over here. This is the electrolytic that separates the tweeters from the other section of the output transformer. This is your output transformer here. This is your EL84, and your preamp, or part of this is the preamp tube, the ABC80. So a lot of the shaping happens on here, and you can see some of those yellow caps on here. This thing had been messed with before, and it was fairly easy to figure that out because some of these components that were soldered in here were a total mess. They were just hanging around in the air. They were connecting properly, but there were extended pieces of wire everywhere. It was a real mess. I've actually used or reused one of the caps. This one here is a cap that was used as a replacement, and it was fine. So I've just connected it properly and I've reused it. As far as resistors were concerned, I think I replaced one on the power amp section because it was slightly out of spec. All the others are well within spec. The resistors are actually very, very good in that regard in this particular radio. So no dramatic changes here except for the capacitors. A lot of them were fairly old, and I'm sure that they had a detrimental effect on the audio. So we have that ready. I'll show you the underside just to complete this section. As I mentioned before, this is the sparsest underside of a radio that I've ever seen. It's very, very easy to work with. Everything is fairly visible and easy to detach and resolder. Here's your EL84 tube. The pins are all accessible and visible. This is the bypass cap, that 50 microfarad. It was slightly leaky, so I reformed it for a few hours and it's back to normal, so I left that in there. Always good to leave some of the original stuff in there if you can. The capacitors were all changed down here, except for a few of these ceramics, which are fine. These are usually just to decouple some of the heater connections. Nothing dramatic. Some of this that's been done here is already part of the AM circuit and previous stage, so we don't worry too much about that. The AF comes in and goes straight through the top as opposed to coming in the bottom here. And then all the connections that are under here support components on the top side. So this having been done, I just want to show you something here. This is one of the preset controls here. This is how the presets are visible on the underside. You then have a little drawing on the schematic. It gives us an idea about exactly how that worked. That's the one side, and we have the other side as well. And here's the other one on the other side. Again, very few components visible here. A lot of it is just connections, and a lot of it goes straight to where the destination points are. So you don't see that much on the actual switching. So the setup I have here is I've got the signal generator producing 100 millivolts RMS signal at 1 kilohertz. This signal then goes into the radio. It goes into the pickup input. I have the pickup button selected here. And instead of a speaker, I have a 5.6 ohm load resistor connected to the speaker output here. And across that, I've got my channel 1 of the oscilloscope. Now let's see what we get. So right, I've got everything connected in here. If I go to the volume control of the radio and I start turning it up, there's my signal. 1 kilohertz. And we can just see where it goes to before it starts clipping. It's starting to get distorted about there. Let's change the range again. So what we have, I've got it on max now, and the waveform is starting to look a little bit strange at the top. So we started to get distortion there. We haven't got clipping yet, but we started to get distortion. Now that's with a 100 millivolt RMS input signal, which is a bit low. So what I'm going to do is I'm going to drop the volume here, and I'm going to increase the signal generator input signal somewhat. That's 200 millivolts, 300 millivolts RMS. That's more like it. That's more like a line signal. So we get no distortion on the input section. Otherwise we would have the clipping already or some sort of distortion on the waveform. So that seems to be fine. Now if I start upping the volume, we start seeing the clipping over there. There we go. It first starts that distortion and then it starts clipping, and it's clipping slightly early on the top and then it follows at the bottom. So it is almost, I wouldn't say perfectly matched, but it's not bad. It's not bad at all. So we have, that's full clipping there. So that means if we have a line input coming in at 300 millivolts RMS, you will expect some sort of clipping if you put this thing in full volume. There we go. Now that starts getting nasty at about 3 volts. Now 3 volts RMS squared is 3 times 3, 9, divided by 5.6 ohms. We're talking about 2 watts continuous here with a sine wave. That's basically what we're getting at the output of this radio, or rather into the dummy load. Now the dummy load is 5.6 ohms, which is about the same as the speaker. That's probably about right. That's probably what you'll get. Then the other thing that you get here, you'll notice if I switch some of those presets, it does affect it. There's the one on the right. That one is intimate highs. This is the jazz and intimate one. If I connect both of them, I get a similar effect. If I go to the left side, to the bass section, there's a solo bass switch. At the moment it's on solo. If I push bass, I'm not getting much effect here. It's on 1000 Hertz, which is beyond the bass range, but you can still see it does affect it. That's the second one on the right, and that's if I push both. So we are getting some tone control. We're getting a very good signal in the output. It's pretty clean. So I will call the power amp stage done, with the exception of a little bit of an explanation as to how these tone shaping circuits work. And to do that, I think what I'm going to do is resort to the SPICE simulator, set up little circuits like that in the schematic, and show you what the result is on the frequency response. Let's get on to that. We have here the input of the audio. It comes from this switch down here. That switch is a switch that switches on either radio coming in from this end or the pickup or tape input coming in from this end. There's your pickup input, 47K resistor. There's our tape input. Those come to pin 7 of that switch, and the output is 8. It comes out of here, it goes through an attenuation so you can get your tape recording level down through this voltage divider. But forget about that for now. This is the decoupling cap, I beg your pardon. And then it meets this arrangement here, which is a combination of resistors and capacitors that acts as a tone shaper. This combination of switches here is one of those push button pairs. This one I believe is the bass side. We'll check in a minute. And it's labeled B1, B1, B2, B2. Now each one, B1 and B2, has 2 sets of switches, different sets of switches. They activate simultaneously, so they go open simultaneously when you activate it, and they go closed simultaneously when you deactivate it, or vice versa, but they act simultaneously, these two, or this pair, and that pair there, B2 and B2, also activate and deactivate simultaneously. So what we have is the signal comes in here, goes through a 330 picofarad capacitor to the top of the volume pot. The top of the volume pot then receives a signal, and the bottom of the volume pot is connected to ground through this 270 ohm resistor, which is practically to ground, right? The signal is then taken off the wiper here to your preamp. So what happens between this point here, where the signal comes in, and that point there where it meets the potentiometer, the volume pot, is determined by this circuit here and this combination of switches. Now, to see what exactly this does, I decided to try a simulation on SPICE. Let me show you. This is the circuit drawn up in SPICE with a few assumptions made here. This is a voltage source which we need for the signal, to simulate the signal. It's a zero internal impedance source, so it's an ideal source. It's not the case, it won't be the case if you have a pickup or your radio signal coming in, but this is just for a comparative analysis of the various positions of these switches down here. So you got your voltage source here, it comes in, meets this 330 picofarad capacitor, and then that goes across and meets this 1.3 meg resistor to ground, which is effectively our volume pot. So that's the basic circuit. Then we have these 3 resistors in series, 3.9 meg, 10 meg, 1.2 meg across that cap. Then we have these switches, B2, B2, B1, B1, with these 2 cross configurations as we have in the other circuit. So basically what we've got here is this circuit here, all right? So what I want to do now is I'm going to simulate a frequency response from 20 Hertz to 20 kilohertz across the circuit with these switches in the various positions. At the moment, we've got both sets of switches open, and if we do a simulation, this is what we get. We get a bass cut. It's not actually bass, it's bass and mids, because this area here is the mid-range of the audio. So this is giving us a bass cut. And I say cut and not a treble boost because this is your 0 dB line up the top here, and you've basically got a reduction and attenuation as you come down in frequency all the way down to about minus 21 dB at 20 Hertz, right? So if we look at where the 3 dB point is here, and let's just change the scale to 1 dB per division, our 3 dB cut point is at approximately there. So if you look at the bottom left, it's 404 Hertz. So 400 Hertz. This thing below 400 Hertz is attenuating more than 3 dB comparatively to the high frequencies. All right? That is with the switches in this position, all of them open. Now what happens if we depress B1, or B2 rather? When we depress B2, both of those are closed at the same time. Now if we do the simulation again, we get a slightly different curve. And what this curve tells us is that you have no cut for the high frequencies, some cut in the intermediate frequencies all the way down to about 100 Hertz, and then it flattens out again. Right? Now if we take this and put this as a 1 dB per division, not 1 millidB, but 1 dB per division, we have a minus 3 dB point here, over here, comparative to the high frequencies, right? So a minus 3 dB line is here, and that is at 520 Hertz, okay? And then it comes down, 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 and it straightens out again at about 50 Hertz. So what we're getting is this cut is happening. The other one was at 400 Hertz, right? This one is at 500 Hertz. So this one's actually cutting bass further, higher up in the mid-range, but it's also allowing some of the lower bass to be less attenuated than in our previous case. We had minus 22 dB at 20 Hertz, right? So this is a different shape, a different tone curve with this button depressed, okay? Now, let's go back to here and let's depress, or rather, let's depress the other one. Let's clear those, and we're going to go to B1 and simulate a pressing of B1 and see what happens, all right? Simulate. We've got a similar situation, but now our 3 dB point over here is at, let's see what that says, 465 Hertz. So again, this has shifted this curve down a bit from 500 and something to 465 Hertz. So we're getting a shift on where the cut happens, but everything that's happening here is cutting your bass and your mid-range, lower mid-range, and even some of your higher mid-range. So this is doing a bass cut, okay? Now, if we go back here and we simulate pressing both of them, which you can do, let's close that switch. If you simulate closing both of them and we simulate that again, right, if we simulate both of them, you've got 0 dB all the way across the line. So if you have both of them depressed, you've got no cut at all. Let me try it again. There we go. So with B1 and B2 depressed, you're getting 0 bass cut. Okay? So that gives us an idea of what these 3 or 4 possible options are. Option 1 is both of them depressed, there's no cut. Option 2 is both of them open, there is a bass cut. All the way down to minus 20 something dB at 20 Hertz. Then depending on which of these you press, you get a lower or higher cut up the frequency range. All right, so you've shaped your tonal balance on the lower frequencies with these 2 switches, right? So that's how this part of the circuit affects the signal. That's why you have this contraption here, okay? That's fairly easy to understand, especially when you can actually simulate it. And I like it because you can actually see a response curve and you know more or less what's happening. It's a lot easier than putting this into the oscilloscope and playing around with different frequencies, because what you're getting in an oscilloscope is, if you measure the dummy load, you're actually getting a whole lot of other effects in here. You're getting the effect of the output tube. That's going to have a frequency response in itself. And especially, your dummy load is resistive if you use a resistive load like I've done there. But especially your output transformer, which is probably not very linear, especially for the age, the time this was done, and the pricing of what a really high quality good response output transformer would be. So your shaping would be completely different, and you get very confused because there's a lot of other effects in here. And the idea of doing just this section by itself, it gives you a much clearer idea of what is happening in the circuit to the frequency response, and it's exactly what I wanted to do here. So that's this section. Right, so let's have a look at this section here. This is just before the grid of the output tube, power output tube, the L84, and we have again another set of switches here. These are labeled H's, H1, H2, H1, H2. Again, if you take this H2 and this H2, it's different pairs of switches on the same switch, push button. So these two activate together, and then that one and that one activate together. And what we have here is we have the signal coming in here from the output of the preamp. This is our preamplifier triode. It comes through a 47K resistor, and we have our signal here at a high voltage level, because this is up in the near the B+. So we couple it with the DC blocking capacitor here, and our signal is then at this point without the DC component. It meets an 820K resistor to ground. It meets a 47K resistor in series. Then it has a 10 nanofarad capacitor here. That meets these three switches. All right? And we'll get to that in a minute. If we go back here then, that goes through a 2K2 resistor to the input of the EL84, which is a very high impedance input. Then if we go down to the switches, we have a 39K to ground, a 12K to ground, and these two switches in series. All right? So if we simulate that, this is what we got. We've got our voltage source, our signal source, again idealized zero impedance, which is not quite the case, but for comparative purposes that'll do. We have our 820 to ground. We have our 47K at 2.2K, and this I've simulated the input of the tube as a 10 mega ohm input impedance, which is neither here nor there. It's very high. And then we have this 10 nanofarad capacitor, which meets the switches. I've put these in reverse. Never mind. It meets H1 through there. So H1 puts that in circuit. H2 puts that one in circuit. H1 and H2 together, short that to ground. So what happens if we simulate this, like we did the last time, and we look at the signal over here? Okay, let's try that. So what we have, let's do it over there. What we have over here is zero attenuation. So with those switches deactivated, there's no effect on the frequency response really. Okay, now let's activate H1. So let's short that one there and that one there. Obviously shorting that one there by itself does nothing because that one's still open, but that one is shorted. So what we've done is we've taken this capacitor and we brought it into action through this 39K resistor to ground. So let's see what happens there. Now we start seeing something, right? We are getting a treble cut, and it's not really treble. This is simulation. Don't forget, these positions aren't exact. It's all relative. But if we do a 3 dB, let's put 1 dB per division here, we're getting a 3 dB cut at about 237 Hertz. Okay, so that's with H1 activated. It lets the low frequency through, and then it starts cutting it, and it shelves at about -7 dB from about 2 kilohertz onwards. So we're getting a cut of mids to highs. My guess is that with the right impedances for the source and the load, this shift will probably be far more to the right, so you're actually getting a high cut rather than a mid cut. This whole thing will be somewhere over here, I presume. But for comparative purposes, this is what we have when we have H1 activated. Okay, so let's take H1 off, and now let's activate H2. There's H2 activated. Let's simulate. Now we've got this shifting to the right. It's shifted to the right. If we do, it's got the same basic curve. The cut is higher. We now have the leveling out down here at about 13.5 dB. And our 3 dB point now is at, it's over here, it's at 277. So it's shifted a bit to the right. Okay? But it's cutting the treble. Now what happens if we activate both of them? So we close that one there and simulate again. Now what we're getting is a treble cut without the shelf. This is infinite. It cuts infinitely, cuts down further as you go up in frequency. But our 3 dB point now, let's try that. Let's do 1 dB per division. Our 3 dB point is somewhere here, which is 323 Hertz. So again, it shifted it up again. So as you can see, with these three combinations of switches, we have three different positions of our tone shaping of the treble circuit. So we get three different treble tones to it. Actually, we get four, because if we leave them both open, we have zero, okay, zero cut. It goes straight through. So that is how that upper section of the tone control works. So the reason I wanted to do this is to get an idea of how the shaping occurs with these different combinations of switches that they've put in. They put one in here and one over there, so we get a better idea of how the shaping occurs. Now, this particular one also has the feedback, and feedback comes from here by the speaker, comes down here, and it goes and meets, if we consider this switch open, it meets a capacitor with a series resistor. Should I say a resistor with a capacitor? Now, when you see a signal coming and meeting a parallel combination of resistor, capacitor, what this is doing is shaping the high frequencies and low frequencies. So across, if this capacitor was not there, this 12K will just act as a resistor, okay, for all frequencies. Now, the minute you put a capacitor in here, and this one's quite high, 150 nanofarad is quite high, what you're doing is you're making this thing less resistive for high frequencies or higher frequencies. So at low frequency, this capacitor is basically open circuit, and all it sees is that resistor. But at higher frequency, this capacitor is an open circuit, so it sees almost no, it's a closed circuit, so it sees almost no resistance. So you're shaping the amount of signal, or rather the frequency of the signal that's coming through here. Now you see the switch here acts as a short to that. Now this is, K is for shortwave. My guess is that with shortwave, you want to cancel any shaping effects. You don't have to worry about hi-fi or anything like that, so your feedback will be a straightforward feedback to increase your frequency response and improve your audio quality. There's no shaping involved. When you open this, that circuit comes into effect, okay? Then what it meets here is, again, a resistor with a capacitor with two resistors in series here, but that all in parallel, with a capacitor and resistor to ground. So this again shapes your tone. I'm not going to simulate this. This is just basically shaping your tone into the feedback path, and it's feeding it to the ground or to the lower section of your volume pot. So whatever comes here is deducted from the total response of the volume pot. If it's negative feedback, if it's positive feedback, it would add. It basically lifts your floor level, your zero level, or reduces your zero level of your volume pot, and affects what tones you get coming out of here through to the preamp. So it's very interesting. These guys did a great job in those days of shaping these tones. They did a lot of shaping. Some of them have variable. Most of the radios actually later on especially have various presets and also a variable tone control. And you can do that very simply. If you wanted a variable treble control, you would just have, say, this capacitor, and instead of having a fixed resistor here, you'd put a variable resistor to ground, going, say, from a very high resistance, say 1 meg, which means that this capacitor would have very little effect, all the way to short when you have your pot turned the other way. And when you have that, you have zero resistance to ground, so this capacitor shorted to ground, and it means that your treble bleeds down to ground. Your high frequencies get through that capacitor, whereas your low frequencies struggle to get through that capacitor, and they prefer to go into the input of the tube. That's how you bleed high frequencies to ground, through a series resistor capacitor combination. Okay, and depending on what the value of the resistor is there, more or less high frequencies go to ground, or rather more or less of the high frequency range goes to ground. So that explains a bit about how the tone circuit works. Quite frankly, this is actually more for my understanding. If you get something from it, that's great. And I hope you enjoyed it. And the next stage obviously is carrying on with the radio stages. Right, thanks for watching. See you soon.